Okay, exam number 2, problem 2, was the graviton or rotor or dropout ride. I did this problem in lecture. It's actually also a homework problem in Ohanian, although I didn't assign it because I did the problem completely in lecture. So in any case, what you've got is, and I'll draw the free body diagram in part E, but I want to give you some warm-up questions, which I was hoping was pretty easy. So you've got a rider who seems to be stuck to the wall as this goes around in a circle about a vertical axis. And the only thing keeping her from falling is the friction force between her and the wall, which points up while gravity points down. Okay, so the first question on this problem was, does it rely on static or kinetic friction? And the answer is static friction. And the reason you have to justify your answer is because the rider and wall don't move with respect to each other. She remains at the same place with respect to the wall adjacent to her, and that's the condition for static friction. If one object is moving with respect to the other, sliding over top of it, that would be kinetic friction. If they aren't, it's static friction. So that was supposed to be an easy 2 or 3 points or 4 points. Okay. Part B, what's the tangential velocity or speed in terms of the other parameters? This was also supposed to be an easy question. You don't have to really solve for anything. You just have to understand what tangential speed is. And you can think of this in different ways if you like. She goes around in a circle of radius r, circumference 2 pi r over the period, or 2 pi rf, because the period is 1 over f. And again, you weren't expected to memorize formula. If you look at the formula sheet, there it is. There, period equals 1 over f. You have everything you need here. V tangential equals 2 pi r over t, t equals 1 over f, or omega r. You're supposed to be comfortable switching back and forth between these various forms. So all you had to do is look at the formula sheet, or remember, or just be able to analyze where the velocity, where the speed is, 2 pi r over t. So that's part B. Part C says, what's the centripetal acceleration of the riders? All you have to know there is that centripetal acceleration is v squared over r, or if you prefer, omega squared r. I like this form, but either one is fine. Omega equals 2 pi f squared, again from the formula sheet if you don't know it yet, but you will later this semester. So you can write it in one of various ways. So that you could write this as 2 pi r f squared over r, whatever you like is fine. But in any case, you should end up with something in the form 4 pi squared f squared r, as like in 4, 2 squared pi squared f squared r is the magnitude, and the direction is just radially in. Would be a good way to describe it. So that's C. Part D, what forces act or contribute to the centripetal acceleration on this ride? Normal force. F centripetal is the normal force. In from the wall. Okay. If you picture this, what is it that's making her go around the circle? Well, it's not friction that's holding her up. Okay, it's not gravity that's pulling her down. She's going around in a circle because the normal force from the wall is pushing on her. If you remove the normal force, that would be like removing the wall. You just go flying off in a straight line. So D is the normal force. Okay, now we get down to the deeper part of the problem. Draw the free body diagram and then solve for the minimum coefficient of friction. That's what I really did in class. And so let's just draw the wall just to get us calibrated. And the rider, we'll just treat her as a particle for now, or a box, or whatever you want. The forces acting on her are mg down, the normal force from the wall, pushing perpendicular to the wall, and the force of friction, F sub F, holding her up. And I'll draw a coordinate system like this, x and y. Okay. So we have three forces: normal force, gravity, and the force of friction. Okay. And that sets us up for doing part F. Okay. Solve for the minimum coefficient of friction needed for this ride to work. So what we do, sums of the forces in the x direction, well, there's only the one. That's the normal force. That has to equal to the mass times the acceleration in the x direction, which is a centripetal force. So that has to be equal to 4 pi squared f squared r times the mass. Mass times acceleration. I just put the mass at the end. The acceleration comes from up here. That's why I had you work it out earlier. Okay, the sums of the forces in the y direction. Okay, that's going to be equal to mu s times the normal force. That's the force of friction pushing up, and I'll just write it as mu s n. Okay, and assume that we're using the maximum force, minus mg down. That's an mg down. Those have to be 0. And now I can plug in for the normal force my expression from up here. So I have mu s times the quantity 4 pi squared f squared rm minus mg equals 0. And this can be solved for mu s. It's equal to 0, by the way, because there's no motion, certainly no acceleration in the y direction. That's our hope. Okay, so solve this for mu s. And we have mg on the right side of the equation divided by 4 pi squared f squared r. And that'll be the minimum coefficient of static friction that will prevent the rider from falling. Something bigger than this minimum will be just fine, even less likely to fall. So that's it for problem number 2.